Okay, so last time we ended the notes with just talking about these practical issues of how do we decide our effect size and variance and difference between the means and so forth when we do a power analysis. Um, Again, kind of like what we talked about this past set of notes about assessing things like normality. There are no easy sets of rules, so you know you always make the right decision. You need to develop some experience and just get some intuition about doing this. So some examples is just getting to know the research a little bit. So for example, if you talk to the scientists and they go, well, if I can show the mutation rate has doubled, that is something big that I'd want to be able to detect. Then you know doubling that rate is going to be practically significant and you'd want to include that as your effect size measure. Okay? If an increase in miles per gallon of one is relevant, then include that as your effect size. Again, these are not statistical issues. These are more practical issues. Again, a 20% reduction in serum concentration of a hormone is going to be a diagnostic result that means something, so design for that, okay? This is essential, and you have to state up front what your effect size is, why you chose that effect size, and then the power analysis that follows. But what about sigma squared? Best case, in my opinion, is getting a variance from a pilot study. Next best is having other past experiments from the literature is reasonable. You can include theoretical variances. Like if you know it's Poisson, well, just report what your assumed mean of the Poisson, hence variance, is. If it's binomial, then think about, okay, worst case on our proportion, it'll be this. You can compute a theoretical variance in times p times 1 minus p. Those are actually easy cases, I think. You can also use some ranges of plausible variance values. That works too. There are some rules of thumb that we can talk about. I don't know how good or bad those really are, to tell you the truth. So suppose you have equal sample sizes and you think that any configuration of means where two means are d or more units apart is going to be interesting, and you get that from the person, from your own expertise or the person you're collaborating with. So the smallest value for that non-centrality parameter from the F distribution is going to be this. It's going to be n times d squared over 2 times sigma squared. So for any two means that have that distance d for its distance, the sample size will, with sample sizes n, that effect will be at least that value there. Thus, the power for any other values of your non-centrality parameter will be at least as big as what you have computed for this particular quantity here. Sample size again. Once you've chosen epsilon and you have some ideas about how to handle the means, and you have a pretty good idea about how to guesstimate sigma squared, your sample size analysis takes those values and finds the smallest sample size that you need for each treatment level sample to achieve a specific level of power. Okay, so you might maybe do this several times. When I work with people in other fields, I'll say, well, if you want 80% power with a 5% level of significance in these effect sizes, you need this sample size. If you want to increase that power up to 90, then you're going to need a few more observations and give them some alternatives. I think that's a good rule of thumb. In principle, this involves power for a lot of different sample sizes. You can go on and do this. It's easy to do in R though. Okay, we're going to take a look at that, by the way. I have code and an example. So right now it's just understanding conceptually what we're going to do in class. We actually need to talk through this output in class, so I'm going to leave it for that. All right, another approach is to use a confidence interval to estimate this. You in particular estimate that margin of error. And the width of the interval, okay? So say you want to pick a certain width of interval for being precise enough, short enough to mean something, well, you can limit that interval width or margin of error easily. So assuming that all the ni's are equal, we can solve for that equation on the previous slide to get this, that margin of error squared in the denominator with this computation here. Of course, we don't know an MSE. You just have to base it off pilot data, past studies, or a good educated guess. Once you know your desired margin of error, we know that the WIs, and we know the WIs, we have a guess for which sigma squared to use for the MSE in particular. Note that we can substitute this in naught using a normal percentage point for the t. And then this gives you a starting point to know something about what that margin of error should be. All right, so we'll see a lot of this material in class. Do come ready also to continue to work on your projects in class this next time.